Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Dafda, and in this 65th video class of DIP, we will study boundary or border following and chain codes in representation for digital image processing and its implementation in Matlab. We are learning the chapter representation and description, and the image segmentation techniques that we have learned in the image segmentation chapter gives us raw data in the form of pixels along the boundary or pixels within a region, but we want those pixels information in a suitable form for representation. So it is a standard practice to use methods that compress the segmented data into representation that facilitate the computation of descriptors, and that we will be learning in representation. So starting with the name, what is the meaning of boundary following? Boundary following means we will be following the boundary or border of the segmented image, and after boundary following we will be assigning chain codes for that boundary or border to compress or compact the data. Okay, and this boundary following and chain codes will be also implementing in Matlab. So let us start. Boundary following is contour following or border following that is used to extract the boundary of an object, and these boundaries are separated from its background by the pixel values, right? So if the object is 1 or the boundary is 1, then the background will be 0. And in our video lecture number 5, we have understood that for any pixel there may be 4 neighborhood or 8 neighborhood. So if there is only straight connectivity, 4-way connectivity is enough, but if the diagonal connectivity is also present, 8-way connectivity is required. These are the steps for boundary following process. First, we have to select a starting point. Normally the top left pixel of the object is chosen as the starting point. Then we have to trace the boundary. For 4 connected boundary following, we have to examine 4 neighbors, top, bottom, left and right. And for 8 connected boundary following, we have to examine all the 8 neighbors. Next, at each step there are certain decision rules. For example, the next pixel is chosen in a specific order, that is clockwise or anti-clockwise. Normally we choose the clockwise direction. The process will continue until the algorithm returns to the starting point, and as the boundary is traced, the coordinates of boundary are recorded. Now let us understand chain codes. Chain code represent the sequence of pixels transitions along the object's boundary, and these chain codes provides a way to encode the connectivity of the pixels in a concise manner. So in the chain codes, each pixels in the boundary is represented by a specific code that indicates the direction to move from the current pixel to the next one in the chain. So chain code will provide us the direction of movement. Let us understand the working of chain codes. We have to choose a starting point, and in the next step we have to trace down the boundary. So as mentioned earlier, the boundary tracing is done in a clockwise manner like this. But the direction numbers for 4 directional chain code and 8 directional chain codes are specified in the counterclockwise or anti-clockwise direction. For example, 0, 1, 2 and 3, and here 0, 1, 2, 3, 4, 5, 6, 7, 0. So remember, the chain code numbers are in the counterclockwise direction, but the boundary tracing that we follow is normally in a clockwise direction. Next, we have to encode the directions, and each direction is assigned a code or symbol. For example, if we choose this top leftmost pixel as the starting point, then we will traverse in this direction. So during the boundary following, we are choosing the nearest pixel for resampling. So this one is that first pixel, next is this pixel, then this pixel. So for this example, we are choosing 8 directional chain code. So for first pixel, we are going towards right, and this right is 0. So we will write here 0. Next we are going diagonally down. So that is 7. So this will be 7. Next we are going down. So for down it is 6. So this will be 6. Here we are going left. So left is 4. So this will be 4. And finally we record the chain. So here our chain code will be 0. So this is how we provide chain codes. So this boundary code formed as a sequence of such directional numbers is referred to as Freeman chain code. But the problem over here is that different starting points gives different chain codes. For example, say this is our object and we are choosing 4 directional chain code. So starting from this pixel, we are going towards right, so that will be 0. Next we are going down, that will be 3. Then left, that is 2. And then up, that is 1. So if we choose this as the starting point, the chain code is 0, 3, 2 and 1. But if we choose this as the starting point, the chain code will be 3, 2, 1 and 0. If we choose this as the starting point, the chain code will be 2, 1, 0, 3. And if we choose this as the starting point, the chain code will be 1, 0, 3, 2. So we can see here that different starting points gives different chain codes. So to normalize the chain codes with respect to the starting point, we have to treat the chain codes as a circular sequence. That means even if you start here, we can go back from 0 to 3, then again 2 and 1. And second point to remember is whichever number gives the smaller magnitude will be considered as the chain code. So in these chain codes, the smallest number is this one, 0, 3, 2, 1. So this will be considered as the chain code for this image. For example, this is our noisy image with the object, and this is the result of smoothing with 9x9 averaging mask. This is the result of thresholding, and this shows the longest outer boundary of the object. This figure shows subsampled boundary, and the points are shown enlarged over here for clarity, and then the points are connected in this figure. So if you want to write 8 directional Freeman chain code for this object, then starting from this point, which is the top left point, for 4 points it is going towards right. You can see here 1, 2, 3 and 4. So the chain code will be 0, 0, 0, 0. Then it is going down. Down is 6. So it will be 6. Then again going right. So right is 0. Then again 6 and so on. So the 8 directional Freeman chain code of the simplified boundary is this. These are the advantages of chain codes. They are compact, they are rotation invariant, and they are simple in processing. Now you may have question in your mind, what is the difference between boundary following and chain code? So boundary following is a process to extract the boundary of an object from an image, and the result of this boundary following is a sequence of coordinates that represents the object's contour. But this boundary following will not specify any particular encoding scheme, and the chain codes are specific representation technique used to encode the boundary information obtained from the boundary following. So boundary following is the previous step of chain code, and chain code, instead of storing actual coordinates of boundary pixels, will represent the boundary as a sequence of codes that will denote the directions of movement. So obviously the chain codes are compact in representation. Why? Because they only store the relative direction information, making them rotation invariant. So these chain codes are particularly useful when compact representation is needed, like in storage or communication applications. Now we want to implement the boundary following and chain codes in Matlab. So we will take this example. This image is a 10 x 10 pixels image in which there are two objects. Object 1 is from 2, 2 up to 4, 4, and object 2 is from 7, 7 up to 9, 9. So this will be the boundary of object 1, and this will be the boundary of object 2. So if we write the 4 directional chain code for object 1, then it will be twice the movement in right direction, that is 0. So object 1 will be 0, 0. Then it comes down 2 times. So 3, 3, because for 4 directional chain code, it is 3 in the down direction. Then it goes towards left. Left is 2. So 2, 2. And finally, it goes up twice. In the up direction, it is 1. So 1, 1. Similar will be the 4 directional chain code for object 2. While the 8 directional chain code will be different from the 4 directional chain code. For object 1, it is going twice towards right, 0, 0. Then it is coming down twice. So down is 6. So 6, 6. Then 4, 4. And 2, 2. Similarly for object 2, this is the 8 directional chain code. So let us implement this in Matlab and check out our answers. This program shows boundary following, which follows the boundary using bwboundaries function. Let us run and see the output. So this is our original image, which we first binarize to obtain a segmented image, and then we find the boundary of the image using bwboundaries. And this is the Matlab program for boundary following as well as 4 connected chain code calculation. So this is the same example which we just understood in theory. So this image is a 10 x 10 image, and the objects are from 2, 2 to 4, 4 and 7, 7 to 9, 9. And we can even see the values of the pixels as 1. So we find the boundaries using bwboundaries, and then we calculate the chain code. Let us run the program and see the output. So this is our binary image, and the 4 connected chain code for object 1 is 0, 0, 3, 3, 2, 2, 1, 1, and same for object 2. And in the output, this is our binary image, and this is boundary followed image. And this is the Matlab program for 8 connected chain code calculation. The program is similar, just the chain codes are different. Let us run and see the output. So this is our binary image, and the chain codes are 0, 0, 6, 6, 4, 4, 2, 2, and the output image that we obtain is same. So that is all in this video class. Thank you very much.